Okay, without any proof, let's just accept this theorem. And it says, suppose that a and b are positive integers not divisible by the same prime. Then the arithmetic progression like an plus b for any n, which is 1, 2, 3, and keep doing it. Then this progression contains infinitely many primes. Okay, be careful. It doesn't mean that an plus b is always a prime. It's not like that. But if you have collection of an plus b by changing n from 1 to 3 all the way, then among these numbers we can find infinitely many different primes in there. Only one condition to get that result is ab must be certain integers is not divisible by the same prime. So even a, b could be composite numbers. The only condition is the prime divisors, but there is no common divisors for a and b. Then this combination always having infinitely many different primes. Okay, that's the theorem here. And the next theorem is, we call that is fundamental theorem of arithmetic. It says every positive integer greater than 1 can be written uniquely as a product of primes, with the prime factors in the product written in non-decreasing order. It's better to state that way, but the key point here is for any positive integer, of course greater than 1, can be written by a product primes, and it should be unique. And this uniqueness gives us all the powers to handling this cryptography. So this theorem is so important and really the basic concepts to develop all the concepts here. And without any proof, let's just accept it. Then the remaining parts of this is just some kind of conjecture in number theory, just for fun. So please thinking about it. The first one is twin prime conjecture. It says there are infinitely many pairs of primes, looks like p and p plus 2. So meaning is the difference between these two numbers are 2. So that's why we call them twins. Okay? And both of them are primes. And for example, how about 3 and 5? And 5 and 7? And 11, 13? Yes. So do you have anything like that? 17, 19, like that? But do you have infinitely many of them? And he says, yes, there are infinitely many of them, but we don't have any mathematical proof of it. So if you can find it, that will be really great. Next conjecture is Goldbach's conjecture. It says every even positive integer greater than 2 can be written as the sum of two primes. Listen carefully, not every positive integer, but even positive integer greater than 2. So it starts from 4. So 4, 6, 8, 10, like that. Then all these even integers can be written by is the sum of two primes. So how about 4? It's 2 plus 2. 6, 3 plus 3. 8, 3 plus 5. 10, 5 plus 5. And so on. And this is famous conjecture, but looks like it's true, but we don't have any mathematical proof yet. Next one is n² plus 1 conjecture. It has some other names, but it says there are infinitely many primes of the form n² plus 1, where n is positive integer. So not every form of this is a prime, but you can find infinitely many different integer n's, which makes this form becomes a prime. That is also conjecture, so meaning is no proof yet. The last conjecture is Legendre conjecture. It says there is a prime between every two pairs of consecutive squares of integers. Squares integer means 2 square, 3 square, 4 square, 5 square, like that. So if you just choose any two pairs of consecutive squares, which means 4 square and 3 square. So let's say it's 2 square and 3 squares. So the result is 4 and 9. then you have 5 or 7 between that. Okay, how about 3 squared and 4 squared? It's 9 and 16, so we have 11 or 13 like that, right? So if you just choose any two consecutive squares, then you can always find at least one prime between those two integers. So this is the end of section 1.5.